Where are they? Where are what? Don't play dumb with me. I know you're doing experiments on moles. No, I don't do experiments on moles. I do experiments with moles. I use them to count atoms. You fiend! Atoms are tiny, and moles have appalling eyesight. It'll take them forever. No, a mole is just a number. They might just be numbers to you, but they're little mole sons and little mole daughters to some little mole mummy. So what are moles and how do we use them in chemistry? Well, let's start with something nice and simple. For example, rice. If we are cooking and we are going to use rice in our recipe, it doesn't say boil 725 grains of rice, does it? Partly because it would take ages to count out that many grains of rice, and partly because we just don't need that level of accuracy. Instead, we count rice in terms of cups. You have 1 cup, half a cup, 2 cups of rice, and everything is nice and easy. And it's the same thing with atoms and molecules in chemistry, except obviously they are much, much smaller. So for example, if this is 1 millimeter between my fingers here, I could fit 1,000,000 molecules between those fingers. And seeing as you can't imagine 1,000,000 of anything, you begin to get an idea of the problem. Very simply, in any normal sample of chemicals in our macro world, our world of centimeters and meters and grams and kilograms, the number of atoms and molecules is just simply uncountable. So, why don't we just take a really big number and all agree on what big number it should be? For example, how about 100,000 billion? All right, that's a super huge number, and we could call it a wazillion. And then we can just count our molecules using that. We can say we've got 1 wazillion molecules, or we've got 1.25 wazillion molecules, or 0.3 wazillion molecules. So why not count atoms and molecules in terms of wazillions? Well, actually, that's kind of what we've done. Except instead of calling it a wazillion, we've called it a mole. So now, instead of having to use these enormous, unimaginable numbers for counting atoms and molecules, we can just do it with moles. We can just say 1 mole of molecules, 2 moles of atoms, or 0.32 moles of electrons. And we just remember that 1 mole is a super huge number. But what super huge number? Is it a wazillion? Well, close. It's actually 600,000 billion. In fact, if we're going to be accurate, it's 6.02214076 100,000 billion. And this number is known as the Avogadro number. Though confusingly, Amadeo Avogadro, who was a chemist that lived about 200 years ago, wasn't actually the person who decided what this number should be. So why do we use a number like 100,000 billion? And why is it 6? And why is it, in fact, 6.02214076? Well, this is where I thought a little history would help us, and it turns out that it's actually way more complicated than I thought it would be. So instead of explaining here, I'm going to explain on another video. But to keep things simple, since 2019, the reason that the Avogadro number has been about 6 with 23 zeros after it is because that's what the International Bureau of Weights and Measures has decided. They're the International Committee of Scientists who decide what our definition should be for our measurements. Things like how long a meter should be, or how much mass should be in a kilogram, or in this case, what the exact Avogadro number should be. So when we're working on the macro scale, this scale of centimeters and meters and grams and kilograms, moles make things much easier. But of course, in our heads, in our theories, in our special experiments, we are working on the scale of individual molecules and atoms. We are working at the nanoscale now. And we might want to think about how many molecules can fit inside a tiny nanoscale cavity inside a crystal. So on that scale, it's much easier to count individual molecules. And we go between those two scales, the macro scale and the nanoscale, by using Avogadro's number. We just multiply to go from individual molecules to the macro scale, and we divide by the Avogadro number to go from macro scale down to the nanoscale. So perhaps the easiest way to look at this is to go right back at least 200 years to the very dawn of chemistry as a science. And this is where Avogadro comes in. He was the first person to say that if we had a certain volume of gas at a certain temperature and pressure, that it would contain the same number of molecules no matter what kind of gas it was. And this was huge. I mean, it was even before molecules had been proven to be a thing. There were still many chemists that were skeptical at the time that molecules and atoms even existed. But what this meant was there was a way now to count molecules. They didn't need to know the exact number, but they could compare numbers of molecules across different elements and compounds. So how does that work? Well, let's have a look. So since we have agreed on how many particles there are in a mole, remember about 600,000 billion, then we can find out what volume that number of gas particles has at a certain temperature and pressure. So for example, at 0 degrees centigrade and about 1 atmosphere of pressure, we've got 1 mole of molecules. And that volume is 23 litres. It's about the size of a small fish tank. Okay? So, now we can do some experiments. And if we look at the kinds of experiments that they did these 200 years ago, this is how they discovered that atoms and molecules must exist. And this is how they built up the foundations of chemistry. So let's have a look at how this kind of experiment might have worked. Let's imagine that we are starting with a balloon of hydrogen gas, and we add some extra oxygen to that gas. Now the oxygen, of course, is going to mix with the hydrogen in that balloon, but just for this little thought experiment, let's imagine that the oxygen stays in a little space all by itself. Okay, so our balloon has got a little bit bigger because we've added some oxygen. We're going to imagine that the oxygen kind of sticks together with its other oxygen molecules. That's not really what happens, but just for this demonstration, let's imagine that. And we've got much more hydrogen than oxygen here, okay? So this is 1 volume of oxygen. We don't need to know the exact numbers. We're going to call it 1 volume. Tell you what, why not just say it's 23 litres, 1 mole of oxygen. Now we are going to somehow light it. We've already set up this balloon perhaps with a metal rod that goes inside that we can have a little electric spark and we can start the reaction going. It's going to explode. We need a very strong balloon, of course. And then the hydrogen and oxygen are going to make water. Where if we cool that mixture back down again, let's say, for example, to room temperature, the water is going to turn into droplets of liquid, and there'll be very little of the volume will be in the water. And now we can look at the volume of the balloon and see how it's changed. And what we find is that our balloon has got smaller. We have lost not just the volume of the oxygen gas, but also some of the hydrogen gas. And it's been replaced by this very small bit of water liquid at the bottom here. And remember, we knew the volume of the oxygen that we put in. And the question is, how much hydrogen have we lost? Well, when we measure the volume of our balloon this time, we find that whatever our volume of our oxygen that we added to the balloon, then we've also lost twice that volume of hydrogen gas. In other words, the volumes of oxygen and hydrogen always react 2 to 1. And then if we take this water liquid and then evaporate it, let it evaporate into a balloon, we will find that our balloon increases in size by exactly 2 volumes. So we have 2 volumes of hydrogen plus 1 volume of oxygen react to give us 2 volumes of water. And this is always, always, always the case. Doesn't matter how big your volumes actually are. If it's 1 litre, half a litre, 23 litres. Whatever volume of oxygen is in your initial reaction, you will react it with 2 volumes of hydrogen and you will get out 2 volumes of water at the end. This was key to understanding that materials must be fundamentally made of atoms and molecules. And this is why the number that we use is named after Avogadro. So, what if our volumes are 23 litres each? Well, then we can easily say 1 mole of oxygen reacts with 2 moles of hydrogen to give us 2 moles of water. And what if the volume is, for example, 46 litres? Well, now we have 2 moles of oxygen reacts with 4 moles of hydrogen to give us 4 moles of oxygen. And we can use this for any number or any volume. Okay, we can use it for half a mole, we can use it for 0.1 moles, and we can just multiply and divide. And then we can calculate how much volume we're going to get, how much material we're going to get, with nice, simple numbers based on moles. But any time that we want to, we can use the Avogadro number to go back down to individual molecules. And that's what makes it so powerful. Here, these experiments are what the first chemists used to see into the world of molecules. Even though molecules are so tiny, we have only been able to see them within the last 20 years or so. Chemists 200 years ago could work out what must be happening on the molecular scale, thanks to being able to calculate down from our macro world down to the nano world. Now we know what happens with volumes of gas, we can now work out what must be happening with individual molecules. The situation must be something like two molecules of hydrogen reacting with one molecule of oxygen to give us two molecules of water. In other words, by using experiments on our macro world and by using moles and then agreeing a number from going between our macro world all the way down to the individual molecular sized nano world, we can do our experiments with balloons and then learn what must be happening with individual molecules. And the power of this is that we can go back the other way too. And when would we do something like this? Well, if we're looking at special catalysts like zeolites, for example. So zeolites are special crystals that have a network of tunnels and cavities. And we can use these tunnels and cavities to do chemical reactions on individual gas molecules. Very commonly, we use them to turn large hydrocarbon molecules into much smaller molecules. So for example, we might have a large butane molecule that finds its way into this cavity. It's in the gas phase, and the walls of this zeolite will catalyze it breaking up, perhaps making methane instead. So the walls of this zeolite are very chemically active, and that means if we have hydrogen gas together with our butane molecule, they can catalyze a reaction where the hydrogen gas breaks it up into smaller molecules to give us methane gas, for example. So now we've gone from one molecule of butane plus 3 molecules of hydrogen gas to 4 molecules of methane. Great. We can study this. We can think about it in our brains. We can put it onto computers and make computer models of exactly how this works. And then we can develop these catalysts and make them far more efficient. Well, that's great, but we want to use these catalysts on an industrial scale. We want to be processing tons of butane gas at one particular time. How do we do that? By using moles. So we scale up from our individual studies on molecules and scale up using moles to be able to work out how can we use this in the most efficient way on an industrial scale. So for gases, it's really simple. We just multiply and divide using molar volumes to get our number of moles, and then we can calculate how many molecules we've got. And we can go back the other way too, of course. But most chemists don't work exclusively with gases. And in fact, most of us use moles as a way of working out how much material to weigh out when we're preparing our experiments, and then to work out how successful our experiments have been afterwards. Most chemists, and certainly me, use solids for preparing our experiments, so we need to know how much of that solid to weigh out. So a very simple way to do it is that if we know how much 1 mole of our chemical weighs, then we can work out how much of that solid to weigh out. So for example, I do experiments with sulfite buffers. Now a buffer is usually a way to control the pH of a solution, to stop the pH from going too high or too low. But in my experiments, I use it as a chemical switch. So I've been doing quite a lot of experiments with this buffer, and I know that I want to have 10 of these hydrogen sulfite ions for every 1 of these sulfite ions. So how can I actually measure that out? Well, one simple way is if I find out how much 1 mole of hydrogen sulfite weighs and how much 1 mole of sulfite weighs, then I can weigh it out that way. So for example, 1 mole of sodium hydrogen sulfite weighs 104 grams. We might say that it weighs 104 grams per mole. The -1 up there meaning per, of course. And 1 mole of sodium sulfite weighs 126 grams per mole. So if I have 1040 grams of sodium hydrogen sulfite and 126 grams of sodium sulfite, then my mixture will be 10:1. Okay, but this is a kilogram of material. Okay, over a kilogram of material, that's going to be a big pile of powder about this big, and I just simply don't need to use that much material. In fact, it's no use to me at all because this buffer reacts with oxygen and goes bad after a few days. So I really have to make it up just before I use it. And in fact, for one experiment, I only need about 0.05 moles. That's about 1/20th of a mole for my experiments. So I just multiply this number by how many moles I want. And I'm going to do that in my head. That comes out as 5.2 grams. Now for my sodium sulfite, that's 126 grams per mole. 126 grams for every mole, but I want 1/10 of the number of moles. That comes out as, do it in my head, so using moles here means that I can work out exactly how many grams of material I need to weigh out to make my buffer. And the reason for using moles especially means that we can take what we know about the atoms in this compound. We've got a sodium atom, hydrogen sulfur atom, and 3 oxygen atoms. We know how much each of those atoms weighs individually, and we just multiply it by the Avogadro number to get our molar mass. Same thing for sodium sulfite. Here we've got an extra sodium instead of the hydrogen. Makes it heavier, look. Okay? So we can use our moles to translate between how many molecules we want to how much mass we're going to weigh out in the laboratory. And we don't just use moles for atoms and molecules. We can use them for all kinds of things. We can use them for photons or for electrons or anything that has a connection to the nanoscale world. So for example, we can take our measurements at the macro scale, measurements of electrical potential, which we usually call voltage, or electrical current, and use those measurements together with the Avogadro number to understand what's happening down at the nanoscale, at the scale of atoms. And we can go backwards, of course. We can take what we know of the nano world and scale that up to design new power systems. Things like hydrogen fuel cells for the coming hydrogen economy. So at the end of the day, we use moles because they make calculations with enormous numbers so much easier. And using the Avogadro number, we can scale up and down between the nano world of atoms, molecules, electrons and photons, and our macro world, the world where we live. So I hope that's cleared some things up for you. And if you want to know where the Avogadro number really came from, then look out for my other video. It surprised even me. And if you have any questions or comments, leave a comment below. If you found this video helpful, click the like button, and if you subscribe, you'll know when the next video comes out. See you next time. All right then. I'll let you off. Just this one time. Oh, nothing. Get back to work.